right, hi everyone. Welcome to a universal hostless substrate for a post-serverless future. This is my second talk today, so if you saw me earlier today, thank you for coming back. This is also, as people have been asking me going around the conference, can I sum that up in one sentence? And it's basically what comes after serverless, right? Maybe not even after, what comes and serverless. Right? So my name is Brooklyn Zelenka. I am XSpeed all over the internet. I am the co-founder and CTO at a company called Fission, where we are working on a lot of the things I'm going to be talking about here. I promise that this is not a pitch for any company. This is kind of isn't it interesting that all of these things are being worked on together and that there's a dozen or so companies trying to integrate them to make life easier for developers and users. I'm a programming language theorist and virtual machine enthusiast. I used to be an Ethereum core developer. If you know what Ethereum is, it's a blockchain project aimed to do computation beyond just currency, to do a number of things. If you're in that space, these are a bunch of the standards I've worked on, and they're now ending up back in Ethereum Classic as well. These days, I'm spending a lot of my time on IPFS and decentralized identities, which we'll be touching on in a little bit as well. But despite all of this interesting R&D stuff, that's lots of fun to work on, we still deal with all the same usual, deployment bugs, seg faults with the CLI, all of that stuff too. So a couple goals to orient with the talk. This is the Polyglot and Fringe track, so welcome to the most fringe talk you're going to see at the entire conference. I'm trying to expose you to a lot of ideas in very broad strokes. We're not going to be going super deep into any particular thing because they're all 1 to 2 hour talks in themselves. So we're going to be covering things at a fairly high level. Nothing here is science fiction. This is all stuff that you can already use today. It's just hard to use. So all of the advancements coming in the next 2 to 5 years, realistically, are around developer experience. So this is a peek at what's coming in the next little bit. And this is not to, kind of push for any, it's fringe, but it's not this fringe, right? So we're not doing any of that. So situating really the entire industry, the waves that we're at right now, today, containers are huge, right? Everyone's using containers. Kubernetes is big. People are, obviously investing in that infrastructure, but also investing in the teams and DevOps and all of that to make it work. It's a fairly course-based approach. The idea basically is instead of having to set up your server totally, bespoke and all of the dependencies and then getting it working on everybody's laptop, we'll just abstract from the OS and all of the dependencies and ship that as in one chunk. We'll just ship the entire thing. And that's great because it's so coarse-grained. There's a few challenges with it. One, there's a lot of maintenance overhead with it. This is why you're seeing these DevOps teams getting bigger and bigger and bigger. And the second major one is it's very difficult to estimate cost. And there's a number of companies that are now trying to estimate cost specifically for containerized Kubernetes use cases. Serverless takes that same model, but basically shrinks it down to individual. All right, then. Shrinks it down to individual functions. So we're still, in effect, containerizing, but it's in a much finer grain. You deploy it to the most popular one is AWS Lambda, and as you can get billed per invocation. It also changes the way you think about your program as well, because now you're thinking in terms of function calls rather than an entire application, its dependencies, and all of these pieces. Entirely out of curiosity, who here is using containers in production today? Anybody using serverless? Cool. And from the serverless people, keep your hand up if you're using a framework on it. That's not, so AWS Lambda is infrastructure, not a framework. Anybody using a framework for it? No one yet. OK, cool. So this presentation is about everything that comes after that. So serverless is just, as we just saw, just starting to do this. There's about 5 or 6, actually not bad, frameworks for serverless already that will work across different providers and platforms and integrate with Node, et cetera. But it's still on this part of the curve. So a native SDK for the web. We all have phones, and mobile app developers have a really nice setup, whether or not you like Xcode, right? Where they have direct access to identity, compute, and storage, right? Right on platform, and they don't have to go and send a request anywhere else to do these things. So it would be really nice if we had that on the web too, in a way that felt like it was just on device, right? So continuing to dance around how exactly we do that, which is the rest of the presentation, the end result of this, the net result is you should be able to go from 0 to production on a plane with no Wi-Fi. You should be able to build the entire thing and use it as if you were a real user. And in fact, when you get on the regular internet, when you connect back to Wi-Fi again, you can route connections directly into your laptop. There is no such thing as a deployment phase. Right? You can, of course, replicate that out to have more power, more replication, because you close your laptop, you go offline. But you shouldn't have to have this extra step. Move data and compute to each other. Right? Today, we're spending a lot of time moving data to compute. There's no reason that you can't do the opposite as well, all while scaling linearly. Something that people don't talk about very often is that there's large parts of the world where there just isn't cloud infrastructure, or very limited, right? So parts of Africa and Southeast Asia in particular, these are growing emerging markets that are currently underserved. And we want to lower the barrier of entry so that anyone can become a developer, provider, and a consumer of apps. So why is this happening now instead of 5 years ago or 5 years from now? And there's 2 big buckets. One is the social and business side, right? Licensing innovation, which is actually fascinating, because that hasn't happened since the early 2000s. Data ethics, which in Europe, GDPR, everybody knows about this a little bit more, but there's a movement to have data ethics licenses as well. And platform lock-in and general profiteering. Nobody likes Facebook right now in particular, but also AWS tends to, and all the major cloud platforms, Azure, Google Cloud, tend to like to lock you into their ecosystem. From a technical perspective, the really big one that the rest of this hinges on is we have new pieces of commons infrastructure. So things that we've seen before are things like DNS and the web itself. And we now have new pieces as well, which include things like public commons blockchains and content-addressable web. Content addressing is new. It is there's a number of forms of this. We'll be talking about IPFS in a moment. There are actual advances in computer science that make these things possible, like changes in cryptography, distributed computing advancements, and especially universality, right? So that we can run things in any environment at any point in time and get back the same answer. Why not now? So why is this 2 to 5 years from now? You may have seen this before. This is the tech adoption curve, right? So we have laggards, who are just getting on smartphones now. We have early majority, which is probably most people in this room. Maybe some early adopters in here as well, doing things that are not totally ready yet. And the people working on this kind of stuff are trying to cross this smaller chasm from innovators to early adopters. So people who deal with things that are just horribly broken all the time and difficult to set up to making things actually usable for people on the cutting edge. So let's talk about commons infrastructure. This is a definition of open source from 2005. It's a lot of people work on it, everyone benefits from it, and people can build upon it, even in a revenue-generating fashion. Right? So that includes how, and we'll talk about licensing right at the very end, but say Mongo relicensed because Amazon was running their stuff and not paying them for it, right? So open source kind of cuts both ways. This is called, at the time, was called commons-based peer production. I think open source is a little bit easier to say. And open networks are, a lot of people work on it, we benefit from it, we can build on it, and it's owned by everyone. By participating, even with competitive goals, you are cooperating by serving the content and running compute of others. So as somebody who has a company that's built on top of IPFS, I don't want other people to not run this so that I don't have competition. I actively want people to be running IPFS because then they will also be serving content to my users, lowering my bandwidth costs. So let's talk about IPFS. Has anybody read about IPFS before? Has anybody played with it? One person, yes, nice. So this is what it looks like in the command line. So you take some text and you pipe it into the interplanetary file system, and it gives you back this hash, which is always the same for that text. And then you can go on any other machine and say IPFS cat, that hash, and you'll always get back the same text. So hello world is very well seeded, as you can imagine. This also works for things of arbitrary length, including media. So this is the cat image that they use in the, as their sort of hello world version. So you can bring down an entire image, video, really anything. So the web as it exists today is predominantly a single source, right? So per file, you have one place to find it, and it's in a server-client model. You can think of this as a key-value pair, or nested key-value pair, where you go up to DNS, you say, myawesomewebsite.com, and that lives at this address, and then it'll go to that address, that IP address, and grab this path to grab that content. So we take physical location and abstract it away with both an IP address and this virtual path. It's called location addressing, and it's very, very focused on the physical network. Right? Say, go over there and get me the thing. It's like saying, go to the house at this address and ask the person who lives there this question. It's also mutable. So if I went to a machine learning talk this morning where it detected your face and what the expression you had on it was, and then drew a funny mustache on you. So today I could upload an image that has my face, and tomorrow at the same address it might be a version with the funny mustache, or a video or a JSON file. It doesn't really matter because at any time it could point at something different. Content addressing addresses this in a few ways. So we have another layer of abstraction on top of this. So we're still using virtual addresses and physical location underneath. But we now put a special relationship between the content and the key. So we hash the content, the entire contents. Actually, we break up the file into about 20 kilobyte chunks, hash all the chunks, and then put it in a tree and hash the top. And if I do that, or you do that, or somebody does it 100 years from now, they'll get the same result. Then we can go out to the internet, or out to the network, and say, hey, someone go get me QM123456, and they'll return you that file. It might be somebody sitting next to you at the cafe. It might be on an Amazon server. If they're sitting next to you at the cafe, it'll serve very quickly. This is focused on the data rather than where it lives. So instead of saying, go to this address and ask the person who lives there, you can say, go ask Brooke for this information. And we still have paths. So it's not just all of these hashes all the time. You can put human-readable paths in there, and we'll look at that in a moment. You can't put, and it's not just a tree. It's actually a directed acyclic graph. So you can have multiple points, multiple pointers to the same chunk. So you also get deduplication and compression built in as well. So we both upload different images, but there's some 20 kilobyte chunk that's the same. We're now able to serve that chunk to multiple people. We can't have loops because you can't construct, you don't know the hash for the entire cycle. Right? So in theory it's possible, but impractical to actually do. This is what the metadata on one of these records looks like. So this is QM123456. They all today start with this QM, which is identifying the type of encoding and the length of just the hash. They're about to change this, and it'll be BAFTY for whatever reason. So in this one, we have data says hello world, and we have a bunch of links. And this is the human readable path part. And those links point at another hash, which gives me another one of these, and we can do this recursively. And then when I go to look this up, we can IPFS cat, IPFS the top one, which we need, and then all the links under it to get the content. Still doesn't look very nice because you need this part. What people are doing now is putting that top bit in DNS, in a text record. So you can then go to a site, it'll look up that record, and then pull down the content for that site. Routing and lookup on this type of a system. So you have, you're sitting by yourself, you have a laptop. First thing we do, you have a hash, you look on your own system. Do you have it? In this case, no. If you do, then there's no point in continuing, right? So you don't in this case. So you're sitting in a cafe on the local Wi-Fi. Does anybody in the cafe have it? So you check with your direct peers on the local network. And in this case, they don't either. So we look at the broader network, and we look at peers of peers. And so these blue ones are people that have the file I'm looking for. Maybe they've recently looked at a website that I'm hoping to look at too. So they have it in cache still. So very popular data gets replicated quite a lot as well, which is nice. So we go to the main network. We do a search. We find the computers that can serve this. And then they stream in like BitTorrent in parallel. Right? So in some ways, some people have described this as Git, because you have all the hashing and the guarantee that it's the same thing, plus BitTorrent. The other nice thing we get from the hashing, because if you change a single bit, it's a totally different hash, is you get file fingerprinting. So especially in an era of deepfakes, we want to know that this is the original image, and we can check that nobody has served us altered content. The namespace is enormous. So even though it's only about 3,400 characters long, most things that would get hashed into that are never going to be created. They're not useful files. So it's extremely unlikely that you'll ever have a collision to the point of it being in the hundreds or thousands of years before you end up with any collision at all. This means that we can stick everything in a single namespace, database records, the stuff in each column. The database itself, all the files on your computer's entire hard drive state as it is today, memory, all of it. You also get deduplication. So if, for example, we run a IPFS gateway, two people upload the same image, we just have to track that two people are trying to keep that image around. We only store it once. If 3 people have a copy of that, then they're going to serve that traffic for us as well. And that will, because it does this BitTorrent-like thing, we also get CDN-like features, which is really nice. OrbitDB is a project that is doing databases on top of IPFS, which is very exciting. So DIDs, decentralized identities. This is something that is for sure happening. This is, zero question marks. It's being standardized by the W3C. It's being worked on by Microsoft. I live in Vancouver, Canada, so British Columbia is our, using an American analogy, our state. They're working on this as well. It's based on public key cryptography, so public-private key pairs. All messages are signed. So we have a very high degree of assurance that it was actually, all the data in the system is authentic. And this gives us a truly universal UUID. So you don't have to go to an OAuth provider anymore, unless we later blend this with OAuth. You can use the same one for everything or associate different IDs together. It's agnostic about how it's backed, so you can have it backed by a regular company like you do with OAuth today, or you can have it backed by DNS or a blockchain. This is one of the places where a blockchain actually really has a clear use case. It does really well in this scenario. You can use it for users, devices, institutions, all kinds of stuff. We use a system called claims. So you go to the bar and you get ID'd, make sure that you're over 18. And they look at your ID and they say, oh, you're however many years old. With claims, the government, for example, can attest that you're 18 years or over. So they can look at this and say, oh, indeed you are allowed to have a drink here. But they don't necessarily need to know your age. So we have a principle of least information, as little information leak as possible. Everything gets signed by a private key, so this can not just be for the institution, like, say, my provincial government. It can even be down to the bureaucrat who did that and say that they had authorization to do that at that time. And we can do this for age, credentials, job history, have your, undergraduate degree signed by the university, all of that stuff. Tracking privacy and recovery. So if you follow what Apple's been doing, they're starting to create an ID per login and linking it underneath. We can do something like that, but in an open fashion, using something called a hierarchical deterministic wallet, where you derive new keys off your previous one. And also use keychains. So if you have multiple devices and you save the key to your secure enclave, which is now built into anyone who has a fingerprint reader on their Mac or Face ID on your phone, you have a secure enclave that you never expose the private key. You just send messages to it to get signed. And then the keychain is you can have multiple of those associated with your main identity. Self-sovereign identity is an extension to this, saying that you can generate, it's just public and private keys. You make these all the time as a developer, right? So you can also generate your own ID. You can make as many as you like, and you can use, in that case, commons infrastructure. So you can use DNS or blockchains in particular. Portable compute. So this is the most serverless part of this talk. So when most people think about serverless, they think functions as a service. You should, in this system, we invert the model a little bit. So you serve somebody a front-end website, and they should be able to run everything locally. This is the part where you get on a plane and you should be able to develop the whole thing without an internet connection. Also without a specialized framework built around it, like when you do local development for serverless. Right? So everything just runs right in the browser. I'm a developer. I have a fancy, expensive machine with a lot of horsepower. My business partner, Boris, runs a Chromebook as his daily driver. And sometimes he wants to test out our Haskell code, and it takes a while to compile. It would be really nice if we could just push that up to something that has more power. Move the, in this case, data to more compute and have it run faster. So say even a student with a Chromebook. Why is rendering slides down to a PDF take so long, or rendering a movie? There's actually a couple companies in that space doing that kind of thing, rendering scenes from a laptop. You push it off to a large computer, and then they send you back the result in a totally seamless way. You don't see it. You can do this in a containerized fashion ahead of time, or dynamically at runtime. So you can statically analyze the program and say, here's some chunk, here's a closure of code, and I can send that off, and as long as it takes less time to run than the network cost, then there's an advantage to running it in that way. And also because this is all moving over IPFS and hashed, if somebody has tried to run that chunk of code before, or that chunk of code is a subset of somebody else's code, then there's no data transfer required at all. It's just already in cache for them. This is great for heavy compute, parallel workloads, and as internet speeds improve, smaller and smaller workloads. Conceivably, you could also have it run on peer machines, but now you need a whole peer network. So again, people working on that too, but then you need to have things installed on your machine. So everything else is stuff that will just run automatically with nothing else installed. So approach and trade-offs. So code as data. This is an idea that goes back to 1958 with Lisp 1. that your code needs to be a symbolic representation of some kind. That means that it's also data, and we can ship it around the same way. So we can hash data, or sorry, we can hash functions as well. We can also take this hashed function and the arguments to it, and especially if you query the functions, so you do multiple layers per argument. And now when I run it as a service provider and get an answer, the next time I can just look it up. I don't have to do the compute again. Right? I can say, this hash came in again. Oh, cool. This is the answer. So we can take all of these compiler techniques that we've been using in GCC and GHC and et cetera, and move them up to web scale. Some people call this the world computer. That's definitely what it's called in the Ethereum space. This is getting generalized to any type of computation. Network latency. So if you're a person with a powerful machine and you can run it locally, your network latency is 0. If you're pushing it across, then there's some latency even for doing the request, obviously. We'll look at a couple of the actual approaches in a moment. The three big ones are trusted, which is serverless. So you can still have classical serverless running in this model, right? This doesn't have to fully replace it. It just makes it easier to do other options as well that will work interoperably with it. So that's a trusted setup. You can do an event-based or two-phase commit, which again we'll look at, or a restricted subset. So total functional programming. There's basically if you take a non-Turing complete subset of a language. So these are things that don't run forever. If it's a loop, it has a counter. That means that it'll stop at some point. For every input, there's an output. And it doesn't do any side effects. So you can't write to a database. You can't post to Twitter, any of that. So the bottom here is the user. Here's the service provider for pure functions. Might also be right on their machine. And here are side effects like posting to Twitter. It's a very simple model. You push this subset up. You get a result back. And if, as part of that, it says, oh, and by the way, here's the tweet to post, then you can post the tweet. Right? Pretty straightforward. You can do this in, a lot of approaches have their own special programming language. There's nothing stopping you doing this with just regular JavaScript or WebAssembly. The kind of static analysis that you need to do ahead of time to check that it's total is very lightweight. So it's entirely possible to do. You might just need some extra tooling to make sure that you're in that subset. The other major approach, the one I like, is to use event streams. So event sourcing. Actually, this might be interesting too. Has anybody heard of event sourcing? All right, good, awesome. So maybe about 2/3 of the room. The idea is you just have a bunch of events in an append-only log, so you never actually delete events. And then you can always replay over them to come up with a current view of how you want to see your data. And you can always blow that aggregate away and build it up again. So in this case, we've abstracted away who's even running it. So we have a base event stream. We have a pure function stream, platform effects, which is things that live in IPFS as well, and then things that are off platform. So again, I'll use Twitter as an example. And these all live in IPFS. So we can still do pure functions and generate an event again that says, the result of this computation was this thing. Now it's memoized. And we can push something out to a side effect or even read from the real world. But we have to do an extra step that says, I commit this to my log. Right? So this is a thing that happened out in the real world. I agree that this happened. This is now my log of things that have happened. And then the last one is things that are on platform. So I put something into the database. Right? So I went into OrbitDB. They have a key value database, and I add a key. And then I commit that occurred, but I get an extra benefit that I can also rewind and say that event never happened. So if I give this to a service provider and they mess it up, I can say, you know what, that didn't happen. let's rewind over that one and give it to another more trusted provider, or run it myself. Encrypted compute, so the next two bits here I'm going to may feel a little glossed over because they're fairly deep, but you can trustlessly send, run, and verify compute. So zero knowledge proofs, this is a way of confirming that something is what you say it is without running the computation yourself. So this example will be an interactive zero knowledge proof. So we have this is kind of the canonical example. You have a Sudoku board and the solution, and you want to prove that you've solved it without giving away the solution. Right? The other example often given is you want to prove that you have more of something than somebody else without showing how much you have. Right? These numbers are just symbols, so it doesn't really matter. We can scramble the symbols if we want, and then hand them to a verifier and say, check that each square has numbers 1 through 9, and then you can pick which square you want to check, or line, or row, and then they check, they say, I want this corner. Cool, great. You reveal that to them, and then you scramble it again and say, all right, pick another, and say, I want this column, and then they can check, yes, all 1 through 9 are there, all the symbols are there. And you do this enough times that they say, okay, I have a very high degree of certainty that you actually did the thing, right? Not 100%, but 99 point some nines. So we can reveal no information while verifying a result. So this is great for trustless compute. Also, even the ML speaker from this morning was saying that they want to do compute over people's personal data without having access to it. Train models on your data without actually seeing your data. So this is one way to verify. The way to actually do the compute, and this is very kind of hand-wavy just because this is a multi-hour talk. So you have clear text, so you have the actual, say, your photo, and you can encrypt it, and now you have your ciphertext, or you can compute and get a result. But we can also do this thing called homomorphic encryption, where you say the structure of the data is the same. So apply a blur filter to my photo, and it shouldn't matter if that's encrypted or not. We should still be able to run compute over it and get a result. The challenge with this today is it's very, very computationally expensive, extremely computationally expensive. So it takes a very long time to run. They're working on getting that performance down. So this is more on the 5 to 10 year part of that 2 to 5 years. But it's very exciting. A lot of people are really, really excited about this in particular. So I promised to talk about licensing, everyone's favorite topic. So first time in 15 years. Why now? Well, cloud providers are making a ton of money off of free open source projects. So Mongo relicensed. Mac OS, the new version, Catalina, now ships with the Z shell instead of Bash. Does anybody know why? Bash upgraded their version of the GPL license, which is a viral license, which Apple is afraid will then affect the rest of the licenses on their system. Z shell is permissively licensed. So they switched out what terminal you have. I also saw this literally last night, right? November 6th. Sentry, which is an error logging system, is also relicensing. They're open source by default, and they're adding protections in their licensing as well. So you can use these as a shield for a bunch of different things. Our current licenses, the ones that, MIT, GPL, AGPL, Apache, they're good, but we need a lot more. My absolute favorite example of this is the anti-996 license. So this is an MIT variant. Does anybody know what 996 ICU is? It's a Chinese term that means work 9 a.m. to 9 p.m., 6 days a week, end up in the intensive care unit. So this license says, if you have this practice of working your developers really hard, or really any of your workers, you can't use our software. So let's think about that in terms of data, right? Facebook takes your data, markets to you, is able to shift opinion, make you feel happy or sad, all of this stuff, right? Based on what shows up in your feed, based on your data. Should they be able to store, resell, et cetera, with your data. Again, in Europe, GDPR already has a lot of this built in, and that's at the government level, but shouldn't we also be doing this ourselves? Why should we even be looking at consumer data at all, right? With a system roughly like I've described, users can own their own data. You can serve them an app, they can load the data in, and you never have to see it or store it on your servers. They can pay for their own storage, or you can pay to have it stored and replicated for them, but keep it all encrypted, so you literally never have access to it, right? So you can't violate GDPR if you don't have any data. So, making life easier. This is what this type of platform can look like. You can have files and database in your global storage, some kind of content address system, doesn't necessarily have to be IPFS. You can have digital scarcity, so this is identity, time checkpointing, access control lists, all of that, identity recovery in blockchain or DNS. And you can have portable compute with primarily WebAssembly, also JavaScript. The main problem with JavaScript for anything dealing with cryptography is it's deeply, deeply insecure. There's a couple efforts to do secure ECMAScript, SES, and the JavaScript lava moat, but it's baked right into WebAssembly. So, for developers, you should be able to build and use your apps locally without having to worry about how does it actually work on production. There's no such thing as deployment. Your local is deployment, or is production. Zero config, because your browser is it. Only serve the app, not the data, and any data you do store, you don't have access to. And we can be very bandwidth efficient, which is very expensive on some providers, by serving each other's content, or even just little chunks of it. And having users serve it to each other as well. For users, you have one login for all your accounts. It might even be baked right into your phone, so authenticate with Face ID. You can have, device-based authentication using public-private cryptography. So it's military-grade security. I just finished reading the Snowden book, and this is literally the kind of security he was using to keep himself safe while he was doing all the collection. Users own their own data, share nothing with you by default. You have flexible functions as a service without pre-deployment. You can pre-deploy them, but you can also do them dynamically at runtime. And have an offline-first, local network-aware application that works even when the internet's down at your local cafe. So that's all really nice technical stuff, but the main advantage of these things is we have a chart here from invisible to high touch and totally custom to commodity. The last 60 years, so since computing really has existed, we've been seeing a decreasing barrier to entry. We started with totally bespoke, single-use applications baked into the hardware, moved to private ownership of a general-purpose system, shared hosting, containers, serverless, and eventually, there's nowhere to go past a universal application. With that, thank you.